and tell you that Tom is a professor of information technology, consciousness, and culture at Princeton University. He runs a bunch of different labs, including their AI lab.
Here too.
And but but I think the way that I first got to know him is as the co-author of this terrific book, Algorithms to Live By. And so when I saw that he was writing another book, um, I sort of couldn't resist, but sort of like reach out and say, love to chat and catch up again, and then figure out how we can help promote the book. And then, so I'm going to try to spend the next 50 minutes or so making a specific case and a few claims. And the specific cases, I'm going to try to, Tom and I are going to try to convince you to, one, read the book and tell your friends to read the book, right? And I'm going to make three cases, right? And so, or three claims. The first claim is like there's a very straightforward way to think about this book, which Tom will explain in a moment, as a history of AI over the last 300 years, and putting AI in the context of sort of a movement that we've been in the middle of, and sort of a grand quest. And I think that is a very valid way to think about it. But I'd almost argue that that historical point misses two other important things. One of them is there's a way that he's decided to write the book as someone, not as a journalist, but rather as a practitioner and a researcher, someone who's a peer with the people who are understanding and figuring out these problems and discovering breakthrough ideas. And in that way, he's got a differentiated perspective on how to think about sort of these problems and how they actually get solved. And so then for both those who are practitioners in AI right now, I think they'll find the book inspirational and surprising. And for those who are like one step away, I think you should think of this not just as a primer on things to learn, but rather also in some ways a recipe of how new things get discovered. And I think we'll see as Tom talks about some of these examples that the normal story that you learn either when you take the intro AI class or when you read the newspaper actually is not quite as useful as the way that Tom is telling the story. And then the last thing that I think is interesting about the book is that it also sits in a broader context of the work that Tom's been doing, right? That Tom's been engaged in this bigger mission of the interaction between how people actually think and computer science. And that interplay has resulted in a number of interesting discoveries he's already made and also a bunch of things he's exploring. And so that's like the broad outline of my claim. I hope everyone is now excited enough to, at least if you've got a chance to buy the free copy of the book, to get it right now, and then see whether I'm right or wrong. And then for those of you who missed out, like sort of be convinced to buy the book anyway. And so with that all set, like Tom, maybe the best way to start is like tell us like that central sort of open claim of the book. Sort of you make a series of claims about how the right way to think about this grand quest, and then we could talk about the structure and examples.
Okay, thanks, James, and thank you, Amy. It's really nice of you to do this and have the chance to talk to people about the book. The way that I think about the book is really providing the long context for our current interactions with AI. I think for a lot of people, AI kind of suddenly came out of nowhere a few years ago. If you know a bit more, maybe you think you can sort of trace it back a couple of decades to started deep learning around 2012. But the story that I tell here is one which goes back more like a couple of hundred years and really has this, path that traces between different disciplines. So it's not just computer scientists, it's not just mathematicians, it's psychologists, neuroscientists, and it's the interaction between these disciplines where an idea might become unpopular in one group and then, it gets passed off to the other group, and then the other group sort of chews on it for a while and then comes up with a new innovation and passes that back. And so the overall story here is one that traces three threads of mathematical ideas that sort of get us to the point where we are now. One is rules and symbols. So, ideas coming from logic and formal languages. One is, I call it spaces, features, and networks, but it's more about thinking about concepts as points in space and then artificial neural networks as mappings between those spaces, a way of doing computation with spaces. And then the third is probability and statistics, really giving us a tool for thinking about how to reason under uncertainty. And these different ideas sort of propagate through different disciplines and then sort of come together to give us, I think, a pretty good at this sense of how things fit together to try and understand how human minds work and some of the principles behind AI.
And then, one of my key claims, and I think one of the key battles, I think for any author right now is like, why is it better for me to read this book than it is for me to go on X right now and read the latest, like, hot take on some AI trend?
I think having all of this information presented in that context allows you to kind of detect some of the patterns that we see over time. So, and this is what I say when I teach my students as well, right? So if I have students come into class and they just want to learn, okay, I want to learn the like 5 things that are the latest techniques in order to solve my problems. And we spend some time going through, okay, what were the sequences of ideas that people used to get up to this point? And part of the reason for that is that you see these kind of moments that rhyme through that history where people would be trying one approach and then that would sort of plateau and then they would need a completely different approach and then they would sort of get a little bit further and then they would that would plateau and you need another approach and then sometimes the approach that you need is the one that you neglected because you were sort of getting all of the juice out of the latest method. And so giving people not just what the latest ideas are, but some of the tools to understand what some of the challenges for those approaches have been historically, some of the ways people have overcome those challenges. That gives you another way of thinking about, in some ways, what might be next.
Yeah, and there's a way in which like you tell the story different than you would have than let's say someone would have written it in a textbook, and also different from what a journalist would have written, right? And I think that that's also part of what makes the book interesting to read. Sort of like I got you gave me a paper copy early and it was like constantly marked up, right? That for me, it felt like, oh yes, this strand connects to that. And like I've never really thought about it this way, or this reminds I feel like the other thing you do is like for those who come from the outside of AI or have like sort of computer science, like I feel like you cover almost everything except for the nature of logarithms, right? There's a way in which like it's self-complete enough that like if you're coming from the outside, you're like, oh yes, actually all of this builds on itself. And there was a way that algorithms to live by, I still contend, is a better intro to computer science than CS50, right? And I think that like part of what's interesting about this book is that it is in many ways a better introduction to AI than probably the way that most of us were taught. And so tell us a little bit about the way that you structured the book in terms of people, and you gave us a big chunks of topics, but also you structured the stories differently than I've usually seen it.
Yeah, so the way that I introduce all of the ideas is through the stories of the people who introduced those ideas into the field. And for each of those people, I think one way that makes it a good way to understand these ideas is that each of those people was kind of grappling with some problem. And this is the the schema for each of these sections is, someone is just like stuck with something or obsessed about something and then kind of has an insight that allows them to get past that. And so I think when we learn something like science, there's a tendency to learn that in a way where it's kind of like a dead field, right? Like if you go to physics
What do
class
you
and you just
mean?
learn,
What do you mean a dead field?
well, if I think of like when I learned physics in high school, and it was like, here's the formulas you have to memorize for all of these, principles and laws, and you memorize them, right? And that that doesn't convey the way in which actually being involved in research works, right? So
Mhm.
when you're actually involved in research, you're grappling with problems. You're looking for where are the places where I could find solutions to those problems. And then you eventually sort of maybe find a path through all of those possibilities that gets you where you're going to be. And if you present it in terms of like, oh, here's the solution, right? In retrospect, those solutions are usually pretty obvious, and you never hear the struggle that gets you there.
Right.
And you don't know what the path of possibilities were, and you don't know kind of like that it wasn't sort of a priori guaranteed that we'd get there. And
Give
so
us an example of one of the ones that you liked.
I mean, one sort of less well-known figure in this relevant history is a guy called Jeff Ellman, who was a professor at UCSD. He was a cognitive scientist, right? So this whole book is about cognitive science, about this connection between computer science, psychology, neuroscience, linguistics, the sort of interdisciplinary fusion that gives us a lot of these ideas. And he was kind of the person who first figured out that a good way to train a neural network to learn a language was doing next token prediction. right? So like based on the sequence of words you've seen so far, predict the next word or the next part of a word. And so all the way back in the 1980s, he was trying to solve this problem. But the story of like how he gets to the point of trying to solve that problem is not one where, he's like optimized his life to be able to do this. It's the story of a guy who, like was a phone freak in his when he was an undergraduate at Harvard, and he sort of got into hacking, and he hacked the Harvard mainframe, and like the FBI came and told him off, and then he got into protesting around, anti-war movement things, decided that what he wanted to do was like teach kids, history, US history in Spanish. As a consequence of like doing a lot of work in Spanish, gets interested in language, and then goes to a graduate program in linguistics because he's like, he reads two books. One is a book by a psychologist that's about psychology of language, and one is a book by Noam Chomsky about linguistics. And the psychology one is like super clearly written. He's like, oh, I totally understand that. And the linguistics one by Chomsky, he's like, I understood nothing of that. So clearly, I need to go to graduate school in linguistics because if I
Right,
don't
right,
understand it, if I got the whole psychology one, then that's not interesting. So anyway, so he gets to this point, and then he's hanging out with the guys who are sort of really like David Rumelhat, who's one of the people who first um, developed the methods that help to move neural networks past sort of being able to solve simple problems through developing the backpropagation algorithm. He's hanging out with Rumelhat, and he's like, how do I make this thing work for language? It takes him a few years. He's banging his head on the wall, and he finally gets it and discovers that just doing this trick of next token prediction is enough to allow the models to learn how to represent the sort of structure of language effectively.
right.
And
And
yeah,
you do a good job of describing next token prediction sort of in the book, right? And I feel like you put all the pieces together to make it understandable. But the vividness of I was just trying to find the Elman like line for like you have this short bio of Elman and like so because I do think there's a way in which you can read the book as the ultimate self-help book in the sense that you read these stories of these people who did very important breakthroughs and like their stories are always such a mess and they're so confusing and like sort of he's like it's literally true like sort of he doesn't quite like Harvard, he's like a sophomore and he like rather than doing his homework he reads the Crimson, finds a weird ad, right, and goes down that line, and there's like a way in which like I think that's both encouraging and a little scary in some ways that like so many of these like big breakthroughs were totally contingent on sort of like these slightly random things. And when you write the story, it feels in some ways much more exciting and a little scary, right? In the sense of
mhm.
like you expose how clear it is that they go left, they made a right turn instead. They would never have thought about this problem again, right? Or, sort of like I think you have this thing around I wrote all the alternate like jobs that these famous people could have been. Like Hebbs could have been a teamster, Hinton might have been a carpenter, right? And
Yeah.
sort of like when you think about that, how does that affect? Well, tell us a little. I mean, I don't know. I feel like there are a couple other. There's so many good stories in this. Like, what are some other like figures that were like surprising and interesting to you?
Yeah, so I mean, another one that I hadn't appreciated the depth of the story is Frank Rosenblatt, who was the person who really made the first neural networks that could learn something in a way where you could prove that it could successfully learn this. And so his story, like he starts out as a psychologist. He's doing pretty conventional psychology, like surveys, and then he kind of gets interested in analyzing data from surveys. And he, as part of his dissertation research, ends up building like an attachment to a computer that can like electronically process surveys, right? So it's like, he sort of figures out the circuits in order to be able to do something where it can sort of rapidly tabulate data. And so now he's one of the only psychologists in the 1950s who understands how computers work
Right,
and
right.
electrical engineering, right? And that sets him up to then become the creator of our sort of, first learning artificial neural networks because he's like, oh, I can try and make a model out of the brain. And, goes off and physically builds a system which simulates that and then, has this intuition that there's a mathematical proof that this could work out and then, sort of works out a basic version of that proof and ends up working with some mathematicians to figure it out. But there was another case of like he sort of had this monomaniacal vision of like this is the thing that I want to exist and I know that it's going to work and I'm going to figure out like how to bring it into fruition and how to show that it works. And in doing that, actually, he wrote a book in the 1960s, which really is a roadmap for everything that comes after. He had multi-layer neural networks. He had templates, which are like convolutional neural networks. He actually, the reason why backpropagation is called backpropagation is probably because Rosenblatt called it backpropagation.
Huh?
And then Rumelhat was reading Rosenblatt, and then Rosenblatt's backpropagation algorithm doesn't quite work, and Rumelhat figures out how to make it work with an important assist from Hinton and another important assist from Leibniz. But
Okay, I'm sorry. Just to be clear, how like one was Hinton born and one was Leibniz born?
so so Hinton was born in the 20th century. Leibniz was born a couple of hundred years before that. The critical thing was that Hinton suggested thinking about that problem as one of gradient descent, right? So thinking about taking the derivative of the loss with respect to the weights, and that was something that allowed Rumelhat to then figure out what that backpropagation rule was. And then Leibniz's assist was that the thing that you needed to have a multi-layer neural network was the chain rule from calculus, and that was thanks to Leibniz.
Right. And just to be clear, the chain rule is the thing that we were all forced to learn our junior year in high school, or I guess whenever you learn calculus, right?
Yeah.
You know, sort of like so it was not. It's sort of there's a way in which like connecting some fairly basic thing that every other kid could have learned and applying it in a new way was interesting.
Yeah.
Yeah.
But the rest of the Rosenblatt story, the other side of that is he kind of like after he wrote that book, he's like, ah, I'm kind of done with perceptrons. And he then got interested in like what happens if you transfer neural tissue from one animal to another animal? Does it transfer the memories? Turns out that doesn't work. So, and then he got interested in like the search for extraterrestrial intelligence, and he couldn't get funding to do it at the university. So he built an observatory in his backyard, and he had like a crew of undergrads who like hung out in his house and ran his observatory. And so it was kind of just like being someone who was willing to take big leaps, of faith
Mhm.
on particular ideas and pursue them. And then that really paid off in, one important case, and
In
maybe
one
led
out
him
of three
down.
cases. In one out of three cases, basically, right?
Yeah,
Yeah.
that's right, which was pretty good. Yeah,
Yeah. Yeah.
yeah.
Eh,
Oh, go on. Yeah.
okay, go ahead. Go ahead.
Well, I mean, the other thing that I learned in doing this was that Rosenblatt was actually gay. This isn't something that was in the historical record. I interviewed a bunch of people who were in his his sort of network of the college kids who sort of hang out with him, and it really changed my interpretation of some of the things that
Mhm.
had happened. Where I think it provided a way of seeing him as a little, sort of he was very much treated as an outsider by the AI researchers, but it was something that I think was a salient part of the rest of his life as well. And there's one moment that it becomes super poignant when you know that, which is he's asked by a reporter for the New Yorker what it is that perceptrons can't do. I'm just finding the relevant section in the book. Um, and his response is, so the reporter asks, um, yeah, what are the limitations of the perceptron? What's it not going to be able to do? And Rosenblatt's response is, love, hope, despair, human nature, in short. If we don't understand the human sex drive, why should we expect a machine to? And that's a
Mhm.
moment that suddenly becomes much more poignant when you sort of know where he's coming from.
Right. Right. And I feel like, okay, so there's a way, and I've struggled to characterize this, but there's a way in which because you're in the field, you've been able to write about these things differently and with a certain command of like the material, obviously, but also because you've learned how to tell stories, right? And I wonder how you thought about the balance, like, sort of, I think you credit, sort of your experience with algorithms to live by around how to write this sort of style. And so I wonder, like, how do you think about putting the book together?
It's that's the way that I find, having taught this material for 20 years, the way that I find helps make students enjoy it. And it's what I enjoy as well. So for me, doing the research for the book was not painful. It was joyous because I really love these sort of stories about the people who are involved in doing these things. And understanding that sort of path of, yeah, like where the ideas come from. So as a researcher, that's the thing that I want to be able to optimize, right? It's like I
Right.
want to be able to put myself in a position to have good ideas and make meaningful research contributions. And one of the ways that you can do that is by reading the stories of how other people did it and sort of thinking about, like what are the kinds of strategies that come out of that. So it's a kind of like meta research, in the way that the stories come through. And then for the people who, cognitive science is in this unusual position where, I talk about in the book, really the sort of birth of that integrated interdisciplinary field was in the 1950s. And so we kind of have this moment where some of the people who witnessed the birth of this new scientific field are still alive. And so
Hmm.
a little over 10 years ago, I started interviewing them. I've sort of been running this oral history project where I record interviews with our, oldest cognitive scientists and really get the stories of their lives, but also the stories of, that important transition. And so for everything from the 1950s onwards, it's really based on those conversations. And so then a story is the very natural way of telling that.
And then now you've got a bunch of your students who are now working at the big AI labs or, sort of around there.
Mhm.
Sort of what do you think they learned from reading this book?
That's a good question. I don't know. Do you mean so the students who've taken my classes know some of the things that are in here, right? But
Right.
your question is like, what would someone who hadn't taken that class be able to get from this if
Yeah.
they'd already taken an AI class
Yeah.
or something like that? Yeah. So I think it's those two things, right? Like I said, the context, the depth of, what's the story behind this thing that you do, right?
Hmm.
So when someone makes next token prediction, their objective function, they can know a little bit about why it is that they're making that the objective function, and maybe what some of the alternatives are, and maybe what the reasons are why that's something that works. But also this, like, yeah, like I said, sort of meta discovery part, right? Of if you then run into a problem in your research in your AI lab and you're trying to figure out how to solve that problem, it's a little bit of a toolbox, both of ideas where you can say, oh, well, 50 years ago, someone had this problem and this was the way that they solved it, right? And uh, a toolbox of methods, right? Of like, oh, this person had this hard problem. What did they do to solve it? So one example is from that Rumelhart backpropagation story. The thing that allowed him to solve that problem was actually taking a nonlinear problem and making it into a linear problem, right? So when you do that, the math becomes easier, and he's able to work out the math, right? And nowadays you can use your automated differentiator, and it's not a big deal. But if you want to discover something, looking for the simplest case, right, and then working through those simple cases is a good kind of strategy for doing that.
Yeah, and I think the other thing that's true is that you see how, sort of the ideas that dominate or seem like they're the only thing do end up in with bottlenecks, right? That they end up in places where they aren't able, like you've got to come up with a different way of thinking, and both that understanding that, sort of that's possible and that oftentimes comes slowly is, I think, part of what's interesting about the book,
Yeah,
you know.
yeah, and that's I think a an important sort of idea here too, which is that often the breakthroughs came from somebody taking an unpopular idea and then pursuing that unpopular idea, to a greater extent than might otherwise have happened. So I think particularly in AI research at the moment, you see a lot of people pursuing the same kinds of ideas, right? There's a lot of
Right.
hype, there's a lot of convergence on a similar set of methods and a similar set of ideas. We're all connected to one another via social media and so on in a way that means that, you're getting constant stimulus of whatever the latest things are, and you're sort of thinking in the mode of thinking about those latest things. But in each of these cases, some of the key breakthroughs in what we now think of as computer science came from
Hmm.
a psychologist taking an idea that was an unpopular or an unworkable idea from the perspective of computer scientists, and then figuring out the next iteration of that in a way that then it could be passed back to computer scientists, and then the computer scientists were able to scale it. And so that actually, these two examples that I talked about with Rosenblatt and Rumelhart are both instances of that. So um, Marvin Minsky, who's a great, AI researcher, he, was probably one of the first people to actually make a neural network that could learn. He
Hmm.
was doing his PhD here at Princeton. On his whole PhD thesis is about neural networks and the math of neural networks. And then George Miller, who was a psychologist at Harvard, and then later part of his career at Princeton, he's actually also the person who did the work that led to the creation of the ImageNet dataset, which then turned into so he created WordNet, which inspired ImageNet, which then led to this deep learning revolution. So Miller like found some money for Minsky to sit in the basement of the psychology department at Harvard and like wire together a bunch of like adjustable resistors and like make a actual learning neural network in the basement. Minsky does this, he tries it out, he gets it to learn some stuff, and he's like does a like back of the envelope calculation of like how big a neural network need to make in order to learn anything interesting. And then he's like, no, this is never going to work because it's like the amount of money that you would need to spend in order to build a neural network that could learn anything interesting is like so much that no one would ever want to do that, right?
Right.
And
Right.
so he, as the computer scientist,
And
sort
so
of
he was desperately right and also desperately wrong.
yeah, so rationally, right, he's kind of like just said, oh, this line of work is not going to work, and he goes and sort of founds like symbolic AI methods, right?
Mhm.
Uh, Meanwhile, Rosenblatt, the psychologist, is like, oh, I just want to understand how brains work. And so it doesn't matter if it's not going to scale. I just want to like figure out what the principles are here and figure out how this goes, right? And then he lays those principles and it turns into something that goes back to computer science. Same thing for backpropagation, where Minsky then subsequently showed these simple neural networks are never going to learn anything interesting, right? And Rumelhat, the psychologist, is like, well, I really want these things to work because this is going to be my new theory of how human minds work. And he's like trying to figure that out. And then by solving that problem, ends up with an algorithm that then goes back and sort of, has all of these implications for computer science. And so I think that's a really important thing too, is it's kind of like having fields that have different objectives, right? It's like multi-objective optimization, right? Having, fields that your sort of loss functions are different, your goals are different. That creates the opportunity for then an idea to have the space that it needs in order to grow into the thing that it needs to be in order to, have that impact down the line rather than just focusing on what's working right now.
Right, right. And then again, like I think the case for reading this book is you will see those threads more clearly than if you just chase the latest news, right? That actually, and then when you see the latest news next week or the hot take 2 weeks from now, then it'll make just so much more sense because you'll see how it fits into this grander set of questions.
And I
Now,
focused here on these neural network examples, but in the book, there's other, like you hear all about logic and formal languages and probability theory and so on. Yeah.
right, right. And then now, like, sort of now after going through this process of writing this book, did it change your mind in any way or surprise you in any way around basically the field that you're in the middle of?
Um, that's a good question. So I had this funny experience where when I started writing the book, I wrote the sort of introduction to the book. And I wrote in that introduction the thing that I've said in classes for 20 years, which is, um, my goal here is so I feel like a lot of the time when you read a book that's in this space, what you're getting is the person's own wacky theory of how things work, right? And it's like
Sure.
the authoritative, I'm going to tell you how everything works, and this is the story of it. And I really didn't want to write a book like that because I think, the idea here is really to surface all of these stories of all of these people who've thought about these things and then provide the context for other people to be able to think about these things in the way that they want to be able to think about it. And so in that introduction, when I first wrote it, I wrote, what I say in my classes, which is there's a lot of questions still here, right? That,
Mhm.
one of the things that unlike if you're taking your physics class where you're going to get the answers, what you get when you take a cognitive science class is that we've done a better job of figuring out how to ask the questions, right? So like that's a lot of the progress we've made is kind of like being able to say, oh, here's one way of thinking about this, here's a way of thinking about this, here's a way of thinking about this. And that's very much true, right? So these different theoretical perspectives, rules and symbols, spaces, features, networks, and probability and statistics, they give us different ways of understanding different aspects of how human minds work and the ingredients that you need for an AI system. But I think the thing that changed for me as I went through that trajectory was by the time I got to the end of the book, I actually felt like, oh, we actually have figured out a bunch of these things. And we do have a way of putting these ideas together It's much more satisfying than maybe it was even like 5 years ago. And
Mhm.
some of that is progress in AI, where it gives us good examples of, how you can make intelligent systems and what some of the ingredients in those systems are. But and some of it is just sort of maturing as a field a little bit and working out, okay, these are the pieces that we need, and then maybe we've got now some ideas about how they fit together.
Yeah. Okay, and so I'm going to spend sort of the last bit talking about how this fits into the broader context of the research you've been doing, right? And then also sort of like I feel like the mission everyone's on. But then before I do that, I'm going to just tell everyone if you've got questions for Tom, put them in the chat, and then sort of we'll be able to address some of them sort of at around 50 past the hour. Um, and so tell Tom, like describe a little bit about like how this fits not within the grand narrative AI, but within the narrative of like the things you've cared about, because you started at that intersection, right? And you initially you're focused on, in some ways, how computer science can teach us to how we can use computer science to explain how people think in ways that don't really make sense. And then now you're sort of doing the other. But if you can talk about that whole narrative,
Well,
it'd be interesting.
it all fits together because the way that I think about the work that I do is yeah, exactly at this intersection of psychology and computer science, and you can think about that in terms of using computer science to understand human cognition, but also looking at human cognition to understand what are the things that might be missing from our AI systems and so on. And so the work that I do is roughly the sort of three threads. One thread is looking at the things that are sort of characteristic of human intelligence. And the way I think about that is less in terms of what the fundamental principles are. I think our human intelligence and AI, the same laws of thought are the things that guide both of those. The fundamental difference is more about the constraints under which human intelligence operates, right? So unlike our AI systems, we can only learn from limited amounts of data because we die, right? We've only got a limited amount of time in the world. We can only use a limited amount of compute because that's all we carry around inside our heads, right? To learn all the things we're going to learn and do all the things we're going to do. And we are limited by the bandwidth with which we're able to communicate with one another. So you can't get around those compute and data limits by sharing data with someone else or pooling your compute resources because the best we can do is make honking noises at each other, right? It's a pretty
Right,
low
right.
low bit rate interaction. Um, and so
But I can
I
show
try and
my
understand,
approval
yeah.
by showing my teeth.
I try and understand some of the things that then allow humans to learn rapidly, to use their cognitive resources efficiently, and to develop protocols effectively for being able to interact in ways that allow us to try and overcome those constraints. And that translates into like thinking about inductive bias, right? What it is that's inside human heads that's missing from our AI systems that allows us to learn.
I'm sorry, what's inductive bias?
So inductive bias from the sort of language of machine learning and cognitive science is everything other than the data that influences the conclusions that you reach, right? So it's what's in the head of a kid that means that they can learn language in with 5 years of exposure to speech rather than the 50,000 years of exposure which you get if you're a large language model, right? Um, and so, yeah, so I'm interested in inductive bias, something we call resource rationality, which is algorithms to live by is about resource rationality. It's saying rather than thinking about rationality in terms of what should you do given infinite computational resources, which is the traditional economist's characterization of rationality,
Hmm.
it's more about what should you do as an agent that has finite resources. And that means coming up with good strategies for, solving a problem, even if they're not the sort of perfect, classically rational thing to do.
And then that was the case where there are a bunch of things that we thought of as ways that humans were irrational, based on the laws,
Yeah,
based on our understanding of economics.
yeah,
And broadly speaking, the behavioral economists were all like, look, people are so dumb. And
yeah.
then you helped explain why it is actually that it might actually make sense for humans who limited.
Yeah, that's right. I think one way of thinking about that is that you can see that people are doing something that differs from your definition of rationality. And one path you can take is to say people are so dumb. The other path you can take is like maybe we were wrong about what rational behavior actually is, right? And that matters if you want to build an AI system, right? Because an AI system, to the extent that it has limits on its computational resources, has to make intelligent decisions about how to use those resources too. And so it's going to end up using heuristics and things like that. And it's probably going to end up with some biases that are maybe similar to the kinds of biases that humans have too. And then I do work on sort of cultural evolution broadly construed, which are these kinds of questions of like, how do people work together? How do we collaborate? There was, if you're an Audible member, we actually had an audio series that explored this called Algorithms at Work, which looks at using ideas from distributed computing to try and understand these kinds of interactions between people.
That's right. Actually, that was a very good audiobook. I highly recommend it. It is a way in which, like, if you thought about algorithms to live by as intro CS, and the one that worked was like intro to distributed systems, right?
Yeah, that's
And
right. Yeah.
it was actually quite good.
Yeah.
Um,
That was a fun project to put together. Yeah.
okay, and then like, sort of now as you look at the context we're in right now, sort of the book talks about ways that people were wrong and new ideas came out. Like, what do you think people are getting wrong? Like people in the industry right now, what are they getting wrong? And what do you wish that they would think about more?
I mean, I'm not sure I'm going to tell anyone that they're wrong, but I think what we can do is calibrate our expectations. So I'd say, I think some of the kinds of things that cognitive science can contribute at this moment are, one thing is just a set of sort of conceptual tools for thinking about intelligence, where um, I think computer scientists are in this funny situation where they built something that they don't understand, which is not normally what computer scientists are doing, right? And they can get a little bit of help from people who study intelligent systems that are complex and, you can't really figure out how to look inside them. You can't figure out what they're trained on, which is human beings. So the cognitive scientist toolkit for studying humans is we actually use this in my lab as a method for trying to understand some of the things that are going on with our AI systems, designing experiments that allow us to figure out, the ways in which they're behaving. And doing that is revealing in that I think it encourages thinking at a level of abstraction which is above, oh, what are the specific mechanisms that you're using for building your AI model, and is more about what's the kind of behavior that we can expect from these AI models based on the ways in which they're trained,
Mm,
based on the things that they're built out of, and we can get some insight into what people have been calling jagged intelligence, right? The sort of the fact that our AI systems tend to be like can be good at one problem and then a problem right next to it they're not able to solve very well, and there's another problem over here they're really good at, and there's something else that they're bad at. And so if you want to figure out what that sort of jagged frontier looks like, then those tools from cognitive science are actually pretty powerful for doing that. I think the other thing that I would say is that we are used to thinking about intelligence in terms of the best example we have of an intelligent system, which is us.
mhm.
And to the extent that we're building things that, because they differ in those inductive biases, right? Because they're finding a solution, but they're finding it with much more data and, in a different way from the way we're finding it. The solutions that the AI systems are finding are not ones that necessarily make sense to us and not necessarily ones that behave in ways that we expect. And so that jaggedness is partly a consequence of the fact that our AI systems are not like us, right? They're different in terms of the amount of data they're using, the computational resources they have. So they're just finding different solutions. And so we should expect some divergence between what human intelligence is like and what our AI systems are like. But if we try and think about AI systems using the lens of human intelligence, it can lead us into traps where we
Right.
think, you know, oh, a system just solved the International Math Olympiad problems. That means it's all over because your friend who could solve International Math Olympiad problems could do all sorts of other things. And if this thing
Right.
is as smart as your friend, then what's going to happen? But in fact, it's kind of just smart in a different way.
Right, right. Okay, and so in about 5 minutes, I'm going to let folks ask the questions they put in the chat. And let me ask just one last question. And this is all part of my broader agenda to convince people that this is not just a good book to read for an overview of how to think about AI, but also, interesting enough, in some ways, it's a story of what it's like to do something like ambitious and breakthrough, right? That like in some ways, if and so for either the ambitious college student or for the parents of ambitious college students, like what sort of advice do you have? I imagine this is the question you're going to get a lot at various dinners full of fancy people.
Um, I do think in these kinds of stories of discovery, one of the things that comes through is just people having a different toolkit from other people, right? Like just having different experiences that you're able to bring. And part of the reason why cognitive science is interesting and exciting as a practitioner is this same thing where you can run across an idea in one field and then realize, oh, there's a way to use this in another field. And that's the thing that's what I love in my research is like when we can build those kinds of connections. And so I would say, yeah, it's I, current generation of pre-college students are sort of heavily optimized for whatever trajectory it seems like they're on. But I think the things that help to lead to things that end up being breakthroughs are often the experiences that you have that go beyond that.
Hmm.
Uh, in my case, a formative experience for me was something that at the time was horrible, which was, I missed a couple of years of high school because I had um, uh, like a sort of chronic fatigue, post-viral fatigue syndrome. And in
Hmm.
that time, when I was able to do anything interesting, I was playing multi-user dungeons, which are like text-based role-playing games. But
Right.
as a consequence of doing that, if you went far enough in that game, you became a wizard, and then you had the power to modify the world around you. And the way that you did that was that, under the surface, this entire world was written in like object-oriented C code. And so, like, as a 14-year-old, I learned, a lot of programming chops and really a way of seeing the world that came out of having a very unconventional experience. And I think, I feel in retrospect that even though it felt horrible to be off whatever track I was supposed to be on, was something that helped me have a different toolkit for thinking about the world.
That's terrific. It's funny. I read this oral history from David Donahoe, who's one of these great statisticians. And he's like, my entire trick is I was at Princeton and I was forced to use Unix early, right? And sort of gave me this whole set of tools that other statisticians didn't have.
Yeah. Yeah, there's not that's I the same thing. I learned a whole bunch of Unix from using the systems. And so when I was in college and wanted to do research, the fact that I could like program in C and administer Unix system was very unusual among psychology undergraduates.
That's awesome. That's awesome. Okay, so we're gonna speed run through a set of questions. I'll just call folks up in the order of the chat. I'll ask Ashish to come up first and ask a question.
Sure. Okay, very quick. Thanks, James. Bringing my little bit of my symbolic reasoning background. Professor Griffiths, how do you square away the idea of a formal theory with fundamental limitations of formal theories, like incompleteness theorems and things?
Yeah, that's a great question. I mean, in practice we don't run into those too much, right? In terms of like the things that we want to explain about human behavior. So I think it's a little bit of an open question whether there's a thing that humans do that would surface, where we hit some of those limits in an interesting way. Most of the examples that I've seen of, things that are sort of questions that you want to ask that are incomputable questions and so on, are things that are like pretty specifically about computing systems. You could imagine that that might impose some kind of limits on theory of mind or something like that. But I think it's not something where, off the top of my head, I'm able to give you an example of something where it's been a problem.
Great. Imran?
Yeah, hi. My question's, I guess, somewhat related to Ashish, which is there have been kind of expensive dead ends in AI before, and some people think that the current trajectory that we are on is a dead end as well. Like historically, how has that resolved itself? Have there been some patterns where people kind of figure out finally it's a dead end?
Yeah. Yeah. I mean, the way I'd characterize it is more like someone sort of breaks through something, right? And then there's a rapid acceleration and then things start to level out, right? So it's not that it's like a dead end in the sense that it's not going to be something you're going to like the things we should worry about would be something where you go down a path and then it turns out that was completely the wrong path and none of the ingredients that you have are things that are useful. But even if you do that in the future, like the things that you learn by going down that path often turn out to be useful tricks for, solving another problem when you run into that problem later on. So I can give you some examples like this. So um, in the previous, the sort of the last iteration of AI enthusiasm, right, was around expert systems. Expert systems were based on this was like 1980s, but based on a technology that was developed in the late 1960s, 1970s, what are called production systems. What a production system is just like a system of if-then rules, where it says, if this happens, then this happens. If this happens, set your goal to this. If your goal is this, then do this, and so on. And in building those production systems, they realized that you couldn't just have like a big list of rules. You needed to have some way of prioritizing and deciding what rules to use. You needed some way of storing the rules and retrieving them. You needed to have some way of like some sort of meta system that's deciding like how to update the rules. And so entire AI systems were built along these lines using what we call cognitive architectures, which was a sort of structure inspired by human cognition, where you could say this is the memory part, this is the part that decides what to execute next, and sort of like breaking these things down in these components. Um, Expert systems kind of hit a wall, right? And people had what was called an AI winter after that. Um, and then neural networks come up as there's two things that sort of come up at that time. One is probabilistic methods, like Bayesian networks, and the other is neural networks. And they're closely related in that some of the things that people who are thinking about neural networks were thinking about then inspired the sort of probabilistic networks. But those solve different problems that you had with expert systems. So the probabilistic approach allowed you to sort of deal with problems where you basically had issues in terms of reasoning about the direction of causality, and the neural networks could work because they could learn things, and you didn't have to sort of you didn't have to sort of hand type in all the rules that you were typing into your system. So, now fast forward another, 30 years, 40 years, we get to the point where we have our AI systems built out of neural networks. But then you start running into this problem where you say, okay, I've got my giant neural network that's my large language model. Now, how do I turn this into a complete AI system? And that large language model, you can actually think of what it's doing as being a little like a production system. It's kind of saying, if this is the context, then produce this. If this is the context, then produce this, but doing it in a stochastic way. And that insight tells you, oh, one way of solving this problem is to make something like a cognitive architecture, right? And if you look at LLM agents, that's essentially what they're doing. They're using the same kinds of structures that were used in those cognitive architectures in the 1980s to then translate the capacities of LLMs into full-scale AI systems. And so I think we're, you know, we're going to keep seeing things like that, where those systems are going to run into a problem, and then the kinds of solutions that we find are things that, look familiar from the history of people trying to tackle these ideas.
Hmm. Hmm. Chris Anderson?
Yeah. As a writer, I was curious as to how you use AI in your writing.
First thing is I try not to. Part of the joy of writing this book was that I got to do it, right? And it really was like that. So the way that I wrote the book was mostly I would spend the week reading things in whatever spare time I had, and I enjoyed, getting into the stories of people and so on. And then on like Saturday morning when my kids were at rock climbing class, I would write like 1,000-word section of the book, and just if I iterated that sufficiently often, it ended up producing a book. But so it was like by the time I got to Saturday morning, I was like ready to have all the words come out of me, and I didn't want any kind of AI system interfering with that. The way that I have used AI is mostly for like brainstorming on sort of constrained problems, right? So like thinking about titles for things, or like coming up with a metaphor, or and it almost never actually produces the thing that I actually use, but just engaging in that process is a good way of kicking me out of a rut.
Great. Michael?
Nope,
I can't
not
hear
sure
you,
we can hear
Michael.
you.
We will go to Shu Hui, and then we'll let you go next, Michael, if we figure out your AV.
Sure. Yeah, so the street is flip-flopping between AI is a bubble, AI is going to take over the world. What's your biggest findings in your research? Like, what is the biggest thing that's important in cognitive science, but it's least present in the current frontier AI systems?
Yeah, I talked about some of the flavor of that, right? Which is that I think we are making really impressive systems that are able to solve lots of problems in interesting ways. But if your expectation is that it's going to be just like a human and it's going to be able to do all the things that humans can do, then you might that seems less likely to be true for me, right? And so I think you can go back and forth on those two sorts of ideas, and I think that uncertainty is one thing that explains how people sort of can be continuously debating this. In terms of current frontier AI systems, one thing that we've seen, so I have a bunch of papers that are sort of using this psychology-based method to study these systems. One interesting thing that we've seen when we do that is that the models are very responsive to their training data in ways that can have unforeseen consequences. I think this is something that whenever we get really good at optimizing something, it has unforeseen consequences. You can think about social media as a good example of this, where they got really good at optimizing the linkage between content and engagement and advertising, right? Something that magazines had been doing for decades, but you could do even better in social media. And that had all of these sort of downstream effects in terms of polarization. I think we're going to see the same kinds of things for our AI systems. Some hints of that we see already. Even though our AI systems are engineered not to have explicit biases, they'll tell you if you're asking them something that they don't think is socially okay. It's very easy to get them to manifest implicit biases. So if you just take an AI system and you give it a list of words, and some of those words are family, home kinds of words, and some of those words are sort of work, office kinds of words, and you say, here's a list of words, here are two names, Barry and Sally. Now put one name after each of these words. It turns out that they'll put Barry after all of the work office words and Sally after all of the home, family words, right? And that's just because they've learned these kinds of associations. One perhaps more worrying thing is that as we engineer our AI systems to be more rational, right? So a lot of the training that people are doing now is sort of reasoning-based training, which is optimized for solving things like math problems. They're going to treat things that maybe we don't want them to treat as math problems. And so we have a paper where we show that if you ask an AI system to just allocate people to jobs, and it has some information about, they just come from different social groups, but it doesn't know anything about what those groups are. It's just sort of like, here are these people from these different ethnic groups. Here are some jobs. You get to see for each person if they're successful in that job, and then you can make a decision next. What it does is optimize by using the information about ethnic groups to assign people to jobs, right? And that's probably not something that you want your AI HR system to be doing, but it's something that makes sense if you're just trying to solve that problem as a math problem, because you've given it some information and it's trying to use that information. So I think these are things where we need to think very intentionally about what it is that we're asking our AI systems to optimize, because they're going to optimize whatever it is that we give them.
So I hope that we've convinced everyone of three things. One is everyone should buy this book. They should buy it for their friends or their friends' kids, because it's just this terrific introduction. Second, we should all follow Professor Griffiths' research and like sort of follow it on archive or whatever. And then third, sort of we should all try to convince our kids to go to Princeton. And so with that, I will turn it over to Amy, who will close out and give some closing comments.
Amazing. Thank you, James. And thank you again, Tom. So I'm just actually going to drop the link in case folks weren't able to see it earlier, just for getting access to the book. As a reminder, I believe the book comes out February 10th, so you won't get it until after that. And let me add that in the chat right now. Okay, great. And yeah, that was pretty much it. But thank you again so much for attending. And if you have any questions, you have our emails. You can send us notes, feedback, and have a great Wednesday, everyone. Thank you so much.
Thanks, Tom.
Thank you.
Everybody.
Bye.
That was fun, right? I mean,
Yeah, that's great. Amy, I think people are asking for the link
Amy,
in the
I
chat.
think you need to repost the link. If people join, folks can't see the link.
Great. Okay. Thank you for letting me know that didn't pop up. Okay, there we go.
Thank you.
So now, does everyone who takes your course then have to buy the book as well now? Is this part of the recommended?
I have to figure out. I'm not teaching the related course for another year, so I can work out how to handle the conflict of interest that involves.
Or you can convince your friend. You can convince whoever's teaching the course now, right? Sort of.
Yeah.
Yeah, that's very funny. Well, thank you for doing this. It was certainly a lot of fun for me, and hopefully it helps the book. Like definitely is one of those cases where it deserves a big audience and lots of people, right? So,
Great. Thank you. I really appreciate it.
yeah. Have a great. Okay, so then so the book officially comes out the 10th, and have the reviews started coming out yet, or?
We have a review from Kirkus, which is just the industry reviewer,
Yeah.
and then we're waiting. There might be a couple of other publications that review the book, so I'm waiting for it.
Very exciting. Well, hopefully everyone's like, we saw it here first, right? So. have a good day. And then yeah, I mean, like I'll be very curious whether like this approach towards telling the story resonates, right? Because it feels like it should, right? It feels like it should.
Yeah, I mean, I like you said, I think with algorithms to live by, we discovered that there was an audience that uh, appreciated understanding computer science through the lens of everyday life, and I'm hoping that this is a similar kind of thing for AI, giving people a accessible, framework for discovering some of these important ideas.
Right. Right. Good.
All
Okay.
right.
Take care.
Good to
See ya.
See you later.